Okay, welcome everyone. Our next speaker for this Quantum Wednesday is Ahmed Darwish from Qoro Quantum, a London-based startup building the software layer that ties quantum processor together with classical HPCs. His talk starts from a familiar frustration. Researchers spend more time on infrastructure plumbing than on research. And Qoro's answer is Divi. And from reading the abstract of the talk, it promises a lot. So I'm curious about the talk, and please welcome Ahmed.
Thank you. Yeah, thank you for having me. So let's start by sharing the slides and we can get into it. All right. So yeah, thank you everyone for chiming in. As for just said, we noticed some common frustration in what quantum researchers and quantum algorithm developers are still facing to this day, despite quite some time writing software for quantum computing. A lot of the open source software nowadays is pretty strong when it comes to getting from point A to point B. However, we see that the path you take from point A to point B can be pretty annoying and can be quite repetitive and actually distract you from what you're trying to do. And so our answer to this is kind of like twofold. One of them focuses on basically the back end that actually executes your quantum circuit, but also on the front end on how you actually implement your quantum workflows, your quantum routines, and how Divi, which is basically our SDK that interfaces with the rest of our stack, can help you focus on the research. And like it says, don't worry about so much about the plumbing and so forth. So yeah, to get into it. So I'll be talking about the execution overhead in a very quickly, just to reiterate over what I just mentioned. And then I will show you examples of three workflows in Divi to also give you an idea of how we think about the programs when they are implemented in Divi. And then we're going to get into a bit of a lower level explanation of how our execution model works, followed by programming sums. This is kind of like a special abstraction that we have in Divi, one that's not exactly very common in other open source software, and one that actually helps you think more ambitiously about what you can achieve with quantum software. And finally, I'm going to be going quickly through our back-end interfaces, the portability options that you have through Divi, as well as some benchmarks and extras that also come with Divi. So when thinking about a quantum workflow or a quantum algorithm, typically you would have some sort of a spec. This spec could be, for example, if you're doing quantum dynamics, could be a Hamiltonian that you are evolving. If you are doing QA, this could be your QBO or your graph that you're transforming into a QA circuit and then submitting. And speaking of QA, this is a variational algorithm that also comes with the need for an optimization loop. And if then you start thinking on more of a meta level of about your quantum execution, you can then have all of those kind of like plugins or additions to the quantum execution that belong to the NISQ era and help actually get more utility from the NISQ era algorithms. An example of this is noise mitigation, for example. Another could be observable grouping. So if you can basically collapse your circuits into fewer circuits if they're observable to mute. This is also something that sometimes you might have to think about if your workflow basically needs a lot of circuits to achieve its goal. And of course, if you are working with gradient-based like optimizers, then you also need to think about the parameter shift and generating this entire batch of the variations of their main circuit. And this is what you can see here in the meme is basically kind of like the first kind of local beat that you have to get through. But then once you actually send the results, send the circuits to the back end and you get the results back, then you need to actually think about post-processing these batch results to get basically the singular value, the singular objective value that you need to solve your problem. And on top of this, this is kind of like a bit of a higher level. So if you have some problem that can be partitioned, and then each partition can be solved separately in its own kind of like quantum routine, then again, this adds another layer of what you need to worry about. But we will get into this a bit later. But yeah, I mean, the common pattern is you generate your circuits, you execute potentially a batch of circuits, and then you reduce the results and repeat in the case of a variational algorithm. So yeah, how does basically our stack address all of this? So as I mentioned, we have Divi, which is our SDK for declaring your workflows and for doing all this kind of plumbing of batching, mitigating, and reducing circuit batches. We also offer Maestro. It's also an open source quantum simulator that supports a lot of the standard simulation mechanisms for quantum circuits. But as I will talk a bit more later about Maestro and what kind of makes it special compared to existing simulators. And we have the Qoro Cloud, which is our basically SaaS service, if you want to call it that, which hosts Maestro. So Maestro can, of course, be installed locally on your machine, but we also host it on our cloud for kind of more ambitious and like higher, like more ambitious executions, ones that require more circuits or ones that require like better circuits. But it also interfaces with several vendors in the quantum ecosystem. Oh yeah, and of course, if you have any questions, please feel free to stop me at any point. So yeah, now to look into some examples, code examples from Divi. So starting very simple, say that you want to run a VQE example. So you would provide the molecule, provide the ansatz, the number of layers of the ansatz, and the optimizer that you want to use for optimizing your parameters, and finally the backend. So this all looks very standard when you think about the quantum program. The only thing here that you get from Divi is just how you basically just declare your problem, and you don't worry about any of the plumbing. And then you call run, and you get the ground state energy as the best loss here. And of course, you can also extract the ground state configuration of your molecule. So this is all very simple, nothing super fancy here. If you want to go a step beyond and say you want to actually have some sort of hyperparameter sweep, some sort of a grid search of for VQE, one where you are changing basically the geometry of your molecule, for example, extending or contracting one of the bonds in the molecule, as well as trying out different ansatz. So you can also describe it in Divi in this manner. So here we have 5 modifications to the molecule, one which is 0, which basically transforms the molecule, like leaves the molecule as is. And here we are testing each of these transformed geometries across 2 ansatz. So 2 by 5, you basically have 10 VQA programs, but that's all really that you need to do to actually run all of these 10 different hyperparameter configurations. So with the same thing, you also call run. And after that, you can inspect this class, this object for the best, for example, the configuration that reproduced the lowest ground state energy, for example. And that's it. You don't need to worry about how each of those separate VQE instances work on their own. Everything is basically happening automatically in the background. For something more interesting, as I mentioned before, if you think about partitioning, for example, say you want to solve the max-cut problem for some graph, a graph that potentially is too big to fit into, say, your machine if you don't have enough RAM for the simulation, or if it doesn't fit on the quantum chip that you have access to. So in this case, you can provide a partitioning configuration where you can set the maximum number of nodes that you can have per a cluster. So a cluster is basically that sub-problem, a subgraph of that bigger graph, and also the partitioning algorithm. So again, it is very declarative here. So you declare your problem, you pass it to this, what we call a partitioning program in Sums, and you choose the quantum routine that you want to use for optimization. So QoA is pretty much the standard, but you also offer iterative QoA, which basically optimizes QoA kind of in one layer at a time, like one layer, then add another layer and optimize, and so on and so forth. But also PCE, poly encoding, which actually helps you save up on qubits by compressing basically the initial kind of one hot encoding into a more efficient kind of representation of your circuit, of your problem. And again, you run past the optimizer, the back end, and you run. After running, you would have the separate solutions of each of your subgraphs that were generated through the partitioning, and aggregates the result to give you the best combination of all these results. And this aggregate result function can be configured to actually help you tune how much effort should be spent trying to fit the best solutions from each of these sub-problems together to give you the final result. And we will get into that in more detail later. And if you're actually already coming from tested or pinning, like one thing that I would like to clarify is that Divi is not exactly attempting to replace them in the sense that we don't, for example, have our own implementation of gates or implementation of circuits. We basically just use tested underneath. That's why we are again just providing the plumbing abstractions needed to execute a quantum circuit. So if you are coming from tested or you're coming from pinning, we have this custom VQE class where you can, for example, pass your quantum circuit from tested and your optimizer back end, and then just continue as before. So we have some sort of integration features with these two libraries. So how is Divi then designed underneath? And so we have already seen like three kind of representative examples of how Divi would look like. So I showed you an example of the program ensemble. This is where you actually declare a problem that then requires multiple instances of a lower level quantum algorithm. So in this case, a VQE, QoA, etc., and coordinates the execution of the circuits coming from each of those quantum algorithms, or quantum programs is what we call them. So basically, a quantum program is a program that's bound to a backend, and it represents kind of like an atomic instance of a quantum routine. So you have seen the partitioning program ensemble and the VQE have a pattern sweep, but we also have a time evolution trajectory, where if you're doing time evolution, you would like to test the same Hamiltonian for different basically time steps. So we can use this class for that. So we have the program ensemble dispatching multiple quantum programs. And then within a quantum program, the lowest level kind of abstraction that we have in Divi is the circuit pipeline. And this is the one that actually takes your spec. As I said before, a spec is kind of like the object that then gets transformed into a circuit and then goes through the execution routine in Divi. So this one would then take the spec. If there's any sort of pre-processing that needs to be done to generate the circuit, the final circuit, it is done. You might then, for example, have a stage that does the mitigation, maybe another stage that looks at the measurement and sees if it can group any of the observables. So basically, a pipeline is this like chain of stages through which the circuits go through until they get to the final result. To the final form, final batch of circuits getting sent to the backend. And they also use the same verb. So you can see here that the example calls run, underneath program calls run, underneath pipeline calls run. And basically, circuit pipeline is what you would use if you would like your own custom control of your circuit execution. And this is kind of like a visual of how this would look like. So again, this is an example of an ensemble. So you declare your high level problem. It generates a spec for each of its sub problems. Each of these specs expand to generate circuits. All these circuits are then batched into a single call and sent to the execution. And finally, you get the results. So you reduce the results from these batches into your singular objective result. And if you are doing optimization, this is sent back, and you continue to keep doing this loop until you're done with your optimization. And Basically, again, just going over what the pipeline can currently do in Divi. So first, it can do mitigation. If you want to do bullet whirling, again, for mitigation, it can do that. If you are working with parameterized circuits and you want to bind your parameters, this takes place in this parameter binding stage. And finally, for the measurements. And one nice feature about Divi is that you can basically do some sort of a dry run through your pipeline to actually have a better idea of how your batch circuit might look like. And an example of this is shown here. So this is for time evolution routine. So for this, of course, you first need to do truthorization to generate the circuits. And this is what was being shown here. So this basically generates 3 circuits. Here you can also see the number of qubits used in the truthorization and the number of terms in your Hamiltonian. If you're doing error mitigation, here we're using an error mitigation technique called QWIP. Quantum enhanced polypropagation is what this acronym stands for. And this basically has a multiplicative factor of 32. So it increases the total number of your circuits in the batch by 32. And QWIP typically requires twirling to work. So if we are doing 8 twirls for each poly in the circuit, then this adds another multiplicative factor of 8. And then finally, in the measurement stage, if you're doing observable grouping, this can actually bring down the number of circuits significantly by having a division factor of 3. And then finally, we end up with 256 circuits for this time evolution program, with an average depth of 24, a depth of 2 qubit gates up to 8, and a width of 2. So again, the width is 2 because it corresponds with the number of qubits that we have here. So yeah, this is basically what you can, this is how you can inspect the pipeline that is being used underneath for your quantum program. And so going deeper into program ensembles, which, as I said, is kind of like our special abstraction that makes quantum algorithms, thinking about quantum algorithms more interesting. So again, just going over the scattered pieces of information I've said before. A program ensemble is a collection of sort of independent quantum programs that all come from sort of the same higher level declaration of a problem. And all quantum programs in the program ensemble basically share one backend, and they execute as a coordinated workload. And the coordination of this happens within this program ensemble class. So the programs don't really need to worry about anything. You don't think they don't need to know how the execution is coordinated. They just pass their circuits to the program ensemble class, and then it does the coordination on its own. And in the end, it reduces their individual results into one aggregate result. And what an ensemble expands over, again, depends on the specific domain of the actual implementation. So for a VQE hyperparameter sweep, it's, as you have seen before, geometries by the number of ansatz that you have. And for the aggregation, it's not exactly an aggregation, it's more of one result per VQE. Similarly, for time evolution trajectory, you get also one result per time point. But for something as the partition program ensemble, you get one global candidate for your graph or QUBO made problem. And coming in version 0.14, so in 0.13 now, we're also introducing some sort of a round-based abstraction of the ensemble. So if you, for example, if you're working with a graph and you partition the graph, you solve it, and then you look at the final result, you can then implement how basically this result can feed into a second round of partitioning and of optimization that then tries to refine this initial kind of solution. And for now, the only concrete workflow that we have that uses this kind of round-based ensembles is LASSQD. This is a chemistry-based routine, which basically looks at a molecule, tries to fragment it into fragments, and then solve each of these fragments separately using VQE, look at the results, and basically does more classical processing to get to the final result. And based on this, you can do multiple rounds until you are happy with the performance of basically the objective value. So Yeah, I mean, this example is basically evolving this Hamiltonian over multiple time points. And the one thing that I would like to point out here is that someone might ask, okay, I mean, is this basically just a for loop of the Hamiltonian over separate time points? Well, in this specific case, you can definitely implement it in that way, where you do like a for loop and you generate the circuits from each of those time points and submit it to the backend. But you would actually be facing multiple problems here, and one of them actually has to do with scale. So the first thing, if you are doing a for loop, then you would be generating pretty much very similar circuits for the Hamiltonian, because the time point that you are passing when you're building your circuit doesn't exactly like modify the circuit at all, at least before you kind of like transpile to the basis gates of your backend. It only changes the parameters of some of the gates. So if you do a for loop and you're not doing any sort of caching, any sort of memoization, then you're wasting time doing redundant work. And after that, once if you do somehow live with this kind of inefficiency and you generate the circuits, you're then stuck again with the problem is that you have to handle like you have to basically keep track of so many circuits, one for each time points, if you're taking this time evolution trajectory routine to its maximum. So if you say if you're testing it across 50 time points, then you have 50 different kind of circuits to track, and we have found that if you do this naively, it can be very inefficient. It can even take up resources unnecessarily on your machine. So yeah, this is kind of just one thing that I wanted to highlight. So yeah, and then what happens during the ensemble, as I have seen in the previous kind of visual, you would have 5 time points. Each time point generates a program, and then you have the pipeline execution, and finally you have a backend which gets the batch from each of those programs. And ensembles also support dry run, so even before you kind of like dispatch a very heavy program, one with too many time points, you can actually then inspect how each program's pipeline would act and how many circuits each would produce. And speaking of kind of scale, we also have ways to control the batching behavior of your ensemble. So, for example, if you are not working with many concurrent programs and you are fine submitting one large job to the backend, which is typically the case when you're working with cloud backends, you would have this ability to just like pass a maximum current, passing like -1 to the configuration. So this way it collects the results, collects the circuits from all the programs and submits them to the backend. However, if you're working with kind of like more limited local resources, you can then say, okay, the maximum number of circuits I want in a singular batch is 50. Or if you want to do things in a very naive way with no batching at all, you can simply turn batching to off. This would basically say, okay, for each program, run, let's send a separate job of its own circuits. But of course, this can result in a very low utilization of your compute resources. So yeah. So just to kind of like reiterate over everything I've talked about, but again, in this slide, from the point of view of a partition programming ensemble, you would first define your problem, and in your problem you would pass a configuration that where you can put a limit of like basically a cap on the number of nodes per cluster, and you would construct a quantum program for each subproblem. You would execute, and then you would recombine the results. And this is basically how it differs from, for example, what you have seen in the time evolution trajectory class. So you can see that the abstraction is very generic. There is not really many differences between how each ensemble is implemented. It's basically the idea of how you can think about the bigger problem, the main problem, and not worry about how each of the lower level plumbing works. And then for recombining partition results, this is where you have also a lot of flexibility in Divi. So of course, if you are working with multiple kind of local solutions in each of your subproblems, recombining them optimally is not an easy problem. It can be computationally very expensive, which is why we have basically we expose different ways of combining your solutions, one of which, for example, is greedy combination, where you basically just get the best from each and you combine them. But for it is not always the case that the best from each local solution will result in the global objective, which is why you can pass this n parameter here. Basically, this one looks at the top n best solutions in each subproblem and then tries each of the combinations across each of the subproblems. So this is kind of similar to beam search, for example, and this of course does not guarantee any optimality, but it is a heuristic that can be very powerful. And for extending kind of like partition in sums in Divi, like if you have your own custom problem that you would like to send through Divi, so if you already know how to partition your problem, then you actually don't need to worry about implementing your own ensemble at all. You just need to implement your own problem and how it can be partitioned. So you declare basically your domains specific objects using the object abstractions in Divi, and then you don't even need to touch the quantum parts at all. So I mean, being a bit more technical about this, you just need to supply 3 operations, basically: how to split the problem, how to map the results into a local solution, and how to score a complete solution. And that's pretty much all you have to do. So yeah, I mean, moving a bit beyond the problem solving or the problem declaration in Divi to the back end. So we have this abstraction, it's called separate runner. It's pretty intuitive, has a singular submit circuits function that you need to implement. And right now in Divi, we have 3 simulators. We have Maestro, which I've mentioned before is our own simulator, as well as Qoro service. This is our cloud platform, and Qistit simulator. This is just a simple wrapper around Qistit's air simulator that you can use for sanity checks and so on, also for noise modeling. So yeah, and because they all implement the same interface, switching between them is very simple. Of course, each of them comes with its own configuration, kind of specific configuration. But apart from this, you can easily just plug them in your own code, and it would run as before. And going a bit deeper into Maestro, so what makes Maestro special is its regression-based estimator. This one basically looks at the characteristics of your circuit, for example, the qubit count, the gate structure, the entanglement kind of behavior based on the gates that are within the circuit. And based on that, it can basically choose the best simulation methods to use for simulating this exact circuit. So the candidates in this case would be state vectors, which is kind of like the go-to option for number of qubits below 25. MPS for very like large circuits with a very kind of like linearly acting entanglement. But we also have stabilizers and p-plot. P-plot is a variation of state vector that basically tries to incrementally grow the state vector, so you don't use up all the RAM immediately if your circuit kind of contains separate clusters, blocks of qubits interacting together. But Maestro also comes with its own noise modeling, so it can model noise such as depolarizing and coherent errors, T1 damping, readout error, crosstalk, and time correlated noise. And the Qoro Cloud the Qoro Cloud backend, it's pretty standard. Same kind of like routines that you'd find in a classical cloud service. So polling the job, predicting the execution result, and of course, Divi doesn't worry about any of the scheduling that it does in the back end. It just waits for the results to come back. So yeah, with this, I would like to go to this benchmark that we have done to see how fast Divi generates circuits compared to the big 3. Quantum is the case in the open source ecosystem right now. So we are comparing against Qistit, Fineline, and Cirq. And basically what we're doing is testing how fast each of these frameworks are for generating a VQE, a QoA, or a trotter instance, like basically time evolution. with grouping, zero noise extrapolation, error mitigation, twirling, and actually binding the parameters. Of course, binding is only relevant for VQ and QA. So yeah, for VQ, for example, you can see that we can be as fast as much as 71 times faster than Diskit. For Pinelane, we're even faster. Circ is the slowest amongst all four. And the trend is kind of very similar across the two other algorithms for time evolution and for QoA. So you can always notice a significant speed up in how fast Divi can generate the circuits for you. And someone might say, well, circuit generation is never really the problem when you are doing quantum research. For example, if you're submitting to a quantum chip, then the queue time is kind of like the bottleneck. Or if you're running, like a very, very heavy simulation task, then again, the simulation is what is the bottleneck in this case. And while I agree with this kind of statement, I think it is true for kind of the scale that we are looking at so far, and also for kind of lightly touched, or let's say very lightly modified quantum circuits. So my point is, what I'm trying to say here is that in the NESC era, we are doing a lot of kind of like micro optimizations to make the circuits first of all as few in number as possible, but also as performant as possible, which is, for example, what we're trying to do with zero with the noise mitigation. And we have noticed that sometimes people would kind of like run their scripts and then they would just wait for it to finish running. And because they haven't actually done any sort of loading, any sort of tracking of what is going on in the script as it's working, we have found out that in a lot of instances, actually, the time is being wasted in the generation of the circuits, all that before even being submitted to basically to the backend. And so that's why this is something that we have focused a lot in Divi. And how we have achieved this is by basically using Diskit's Rust-based representations of circuits. So Diskit has this DAG circuit representation, which represents the circuit operations as a graph. And while Diskit only uses this kind of representation for making their transpilation routines more efficient, we have kind of decided to appropriate this object to also represent circuits and the higher level operations on them, such as you have seen, maybe folding the gates, folding the operations for zero noise extrapolation, or maybe twirling. So finding the operations in the circuit to twirl and then generating a copy of this graph with the modifications applied. So yeah. With this, I would like to quickly go over some extras that we also have in Divi. So yeah, first of which is the optimizer landscape diagnostics. This, of course, is more relevant to variational quantum algorithms. So if, for example, you're doing a QoA algorithm and you would like to understand the landscape, the optimization landscape of your routine better, we have this one. That this is an example. We have the scan PCA function that you can easily call on the QoA routine after you are done optimizing it, and then call plot. And this shows you basically how the objective value of QoA has kind of moved in this two-dimensional projection of the parameters of your QoA. And in my opinion, this is very fancy. Like if you're dealing with a lot of parameters, this kind of helps you boil down the change in the values of all of these parameters across only two dimensions. So you can see the optimizer working, slowly trying to find the minimum in the landscape that the optimizer has basically looked at. And we have things that are even more ambitious. For example, Fourier analysis of the parameters, also looking at the Hessian, the Hessian during the optimization. So yeah, this is something to play around with if you're trying to understand the numerical specifics of your optimization routine better. And on in addition to that, we also have Divi AI. So this is a command that you can basically run in your terminal. So and it's like shipped with Qoro by simply just adding AI to the installation script. You get the Divi AI command. It is not exactly a model. It's basically an index of our code and documentation. So once you kind of like run this command, you will be prompted to choose a model to actually run. And this depends, of course, on your machine and how much RAM you have, what kind of processor you have. And basically it downloads the model, and then you have access to this chat interface immediately. And the nice thing about this is that it doesn't require any GPU at all. It's a CPU only model. So of course it comes with this kind of limitations of how much it can do, but if you're too lazy to look at the code or too lazy to look at the documentation, this can help you get started very quickly. However, if you're using one of the more established code agents such as Claude or Codex, the library is also indexed on context 7. So if you're using an MCP, you can point them out to our library, and then it can actually help you write your own Divi programs or even debug ones that you might already have. So yeah, to sum this all up, we, as I said, we take care of the plumbing. So from a problem to a circuit, we have QA, DSP problem, a master problem, or whatever. If you're coming with your own discrete or binary circuit and you pass it to the custom VQA class, we are doing the low-level plumbing of grouping, mitigation, welding, binding, and also the batching, as well as kind of the seamless transition from local prototyping to HPC to cloud to QPU. And kind of like to give you a stronger idea of where you might fit in exactly in what Divi is offering. So if you're starting from scratch, you're still starting out with a new kind of algorithm that you're developing, or basically a new formulation of a problem that you're passing to QOA, or a problem, as I mentioned before, a problem that you're partitioning. So you can start working with the abstractions that we have immediately. If you already have your circuits, then you can use custom VQA to pass the circuits to, or you can even just pass the QASM to the backend directly. You can do this. And for example, if you are maintaining a quantum library of your own and you simply don't want to you don't want to reinvent the wheel when it comes to the plumbing that we have been talking about, and you just want to delegate, then it would be my recommendation to look into the low-level circuit pipeline of abstraction through which you can pass basically the spec or basically the finished circuits from your own library, and then let Divi do the rest in its own pipeline stages. Yeah, so these QR codes are for everything that you would need. So you have the source on GitHub, you have the community Slack if you actually end up needing any help with Divi, and also the dashboard. And that would be it for the presentation. I would quickly switch to a live demo. And so we are here. All right. So again, this is a max-cut problem example, which I have set up on a 20 node graph. And the partitioning basically has a cap of 4 nodes per partition. We're using QOA, 1 layer with Kubila optimizer, 5 iterations. We also have ZNE, and then we are running all this. So by clicking on execution, you can see here how the whole graph is actually being partitioned. And then for each of those partitions, we end up with 1, 2, 3, 4, 5, 6, 7. So 7 partitions, 3 are here, and the other 4 are hidden in this view here. And for example, if you look at this pipeline of partition P0 here, so here we have 5 edges, which would map to 5 circuits, each one measuring its own observable. So just move this over here. Yeah. So this is the decomposed Hamiltonian in the trotter spec, which basically does the trotterization of the Hamiltonian, of the cross Hamiltonian. We don't exactly have any pre-processing for QoA, but then we have quantum error mitigation, basically three scale factors for the Z and E folding. So we move from 5 to 15, and then we have observable grouping. So this maps to only 3. And since we are using Kubila, so this is like a single parameter per optimization loop optimizer. So again, we have a multiplicative factor of 1 here. So we end up with 3 circuits being submitted per iteration. And it's pretty much the same number for the other clusters. And all this goes through the patch coordinator, which basically collects all those circuits and submits 21 circuits per iteration, sends it to the local backend, gets the results back, fans them out again to each of the pipelines, and finally we get the final result. So as you can see here, the final result is that a quantum cut is 34. So yeah, you can also play around with this demo however you want. So you have this, we were just at the graph optimization, but you also have chemistry. If you want to play around with a different molecule, so try and, for example, the bond length, or doing the sweep if you want to sweep across different points. Quantum dynamics for time evolution, and machine learning if you are doing training to quantum neural networks. So yeah, by just following the QR code that I've shown in the slides, you can play around with these demos before you go ahead and basically install Divi and play around and getting your hands dirty there. So yeah, that would be all from my side. Yeah, thank you, and looking forward to your questions.
Yes, thank you, Ahmed. Yeah, are there any questions?
Well, hey, Ahmed, this is Barry. Can you hear me?
Yeah.
Hey, well, first of all, thanks so much for the presentation and the demo. Learned a lot. Yeah, I mean, the problem you speak of, I certainly ran into it when I was first getting my hands on quantum circuits and stuff. I spent so much time trial and error just trying to get the environment harness set up with Qiskit and air and everything else. And so I've certainly can relate to the frustrations of just getting the environment pinned correctly. I was wondering, with Divi handling a lot of the plumbing in the front end, I'm just curious if, because you said it's Qiskit underneath is sort of the engine. If a researcher wanted to run a circuit, but they're like, hey, I'm not sure if this would run best on like an ion Q type of QPU, or maybe Rigetti or whatever, is there a way to kind of do some optimization to figure out, hey, what type of QPU is best? Is this best run on a superconductor or ion trap or whatever? Does Divi have any kind of that functionality?
I would say no. So far, we have only looked into which simulator is best for your circuit. But when it comes to the actual choosing between different forms of hardware, we haven't really delved into any exploration in this part.
One follow-up question. So let's say somebody is running on, IBM Quantum Cloud, and a researcher's like, I really want to run this on. They might need to specify that they want. I forgot all the different bird names, but there's the different classes. Like, hey, I need to run this on a Heron class, and specifically, I would love to run this on IBM Brisbane, or they'd be like, hey, I want to compare this QPU to that QPU. Does it have that kind of functionality to figure out, hey, what if I know the modality, but I want to specify like a certain class of QPU?
Yeah, so definitely interface with IBM institution kind of interface for running on their QPUs. So you can easily provide your own API key. We can help you set that up, and then you can specify the actual device that you run on. Actually, one kind of benefit that you can get through our cloud, one thing I forgot to mention, is that if you're running some circuit and the circuit happens to, if you're running a batch of circuits and those circuits happen to be small enough to fit, to be packed within the same quantum chip, we also provide this functionality. So say you have like a 100 qubit chip and you're sending 5 20 qubit chips, we would pack all these into the same job so that queue time actually is reduced. This is kind of just a tangent. on the topic of your question, but I thought it would be worth bringing up.
Okay, great. Thanks.
Any other questions? Maybe I have a quick one. So I guess all these algorithms you're focused on, things like VQE, QAA, are all focused on these NISC devices. So the programs are all just working with noisy qubits. Do you have fault-tolerant versions of these algorithms on the roadmap, or are you not thinking about that at all?
I mean, not in the short term, because obviously we want to interface and integrate with the current state of available hardware. And that's what we have been spending, putting all the effort into, just trying to get the most out of the algorithms that can run today.
Makes sense. Let's see, any other questions? I guess if not, yeah, thanks again for the talk. And yeah, see you maybe next time in another Quantum Wednesday seminar.
Thank you for having me.
All right, thanks so much.
Bye-bye.